We now discuss the solution of the problem from the section Differential Calculus. And this problem is on the number of distinct real roots of the given equation. This question has appeared in the joint entrance examination main held on 24th June 2022 in the second shift. The problem is the number of distinct real roots of the equation x to the power of 7 minus 7x minus 2 is equal to 0 is. We are given four options. Option A 5, option B 7, option C 1, option D 3. We now discuss the solution of the problem in detail. Let f of x is equal to x to the power of 7 minus 7x minus 2, where x belongs to R. That is, the domain of this function is the whole of the real number line. Now, note down that this function f of x is continuous and differentiable everywhere because it is a polynomial function. And to talk about its critical points, we first differentiate. F prime x is equal to 7 into x to the power of 6 minus 7. Take 7 common, x to the power of 6 minus 1. And this is written as 7 into x square whole cube minus 1 whole cube. And apply the formula for a cube minus b cube. That is, a cube minus b cube is equal to a minus b into a square plus ab plus b square. And that will be equal to 7 into x square minus 1 into x to the power of 4 plus x square plus 1. And further factorization will give you 7 into x minus 1 into x plus 1. And note down that this x to the power of 4 plus x square plus 1 is irreducible over the real number line. That is, it has no real roots. And f prime x is equal to 0 will give you x is equal to 1, x is equal to minus 1 and plus 1. These are the critical points of the given function. So x is equal to minus 1 and plus 1 are the critical points. We discuss further in the next slide. These critical points will subdivide the domain of f. The domain is the whole of the real number line into non-overlapping open intervals minus infinity to minus 1, open interval minus 1 to 1, and 1 to infinity. So this is what we have. Now we determine the sign of f prime, the derivative, by evaluating f prime at a convenient point in each subinterval. And f prime will be evaluated at a convenient point in each subinterval, and then decide the sign of f prime. On the base of sign of f prime, we discuss the behavior of f. The results are summarized in the following table. So first, in this subinterval, minus 2 is the convenient point we have taken. F prime minus 2 is greater than 0. Yeah, that means sign of f prime is positive. Therefore, f of x will be an increasing function in this subinterval. So it's an increasing function in this. And in this subinterval, the convenient point is 0 and f prime 0 is negative. So it is negative. So in this interval, the function is decreasing. Yeah, great. And the convenient point is 2 and f prime 2 is positive. So this is plus. Sign of f prime is plus positive. Therefore, in this subinterval, it is increasing. So it is increasing and attains maximum at minus 1 and then decreases at x is equal to 1. It will attain the minimum and then increases in 1 to infinity. So the function is increasing in minus infinity to minus 1, decreasing in minus 1 to plus 1, increasing in 1 to infinity. Now we discuss the nature of the curves and discuss about the real roots in these subintervals. Now, first we talk about f of minus 2. That means to the left of minus 1, minus 2, f of minus 2. So minus 2 to the power of 7 minus 7 into minus 2 will be negative. Negative. F of minus 2 is negative. Fx increases in minus infinity to minus 1 and attains maximum f max at f of minus 1. So put x is equal to minus 1 in this, you'll get 4. And that means this is your x-axis, y-axis, minus 1, plus 1. And it takes negative at minus 2, negative, and increases and takes the maximum f max, that is equal to 4. So the graph of fx crosses x-axis here, x-axis, x-axis. That means fx is equal to 0 equation has real root in minus infinity to minus 1. Agreed. And now second, in the second subinterval, so f of minus 1 is 4, which is positive, which is maximum. Fx decreases in minus 1 to plus 1 and attains minimum at f min, f of at x is equal to 1, that is f of 1 is minus 8. So it will attain minimum here, here. So the graph of fx crosses the x-axis. It crosses the x-axis. So this crosses the x-axis. Therefore, f of x is equal to 0, the equation has real root in minus 1 to plus 1. Agreed. And in the third subinterval, f of 1 is minus 8, that is f min, which is negative. F of x is increasing in 1 to infinity, and f of 2 is positive. Therefore, it crosses the x-axis again. So it crosses the x-axis again. So the graph of fx crosses the x-axis, and what is that? This here. Therefore, f of x is equal to 0 has a real root in 1 to infinity. How many distinct real roots are there? 3 distinct real roots are there. So thus the equation x to the power of 7 minus 7x minus 2 is equal to 0 has 3 real roots. Let's look at our options. Our answer that this equation has 3 distinct real roots appears against option D. Therefore, that is our answer for this question is option D. And that is the detailed discussion of the solution of the given problem from the differential calculus, and to discuss about the number of distinct real roots of the given equation. I am sure that you have understood the solution of this problem. I wish you all the best. Thank you.